Write the expression for the volume when the area bounded by the f of x equals x squared minus 8x plus 17. So that represents the green parabola, the lower bound. And g of x equals negative x squared plus 8x minus 13, which is the upper bound, okay, which is a blue parabola. That area is going to be rotated around the x-axis, and it's going to generate a solid. And we want the expression for that. So first of all, if we take a look at this area, that yellow area, if we rotate it, it's going to kind of give us a shape that looks kind of like this. So I'm going to try to sketch it in. So it's not super easy to sketch in, but there is the top half of the parabola. That is, sorry, the inside of the shape that we're going to generate. There's the outside. And so the outside radius is going to generate this circle around the outside like that. And then the inside radius, that green line, is going to generate a circle on the inside kind of like that. And what we're going to end up with is this cross-sectional area, which is going to be represented by this washer. Okay, so I've drawn the washer on the side here. And to be able to get this cross-sectional area, we need to be able to find the area of the circle, the big circle, and subtract the area of the small circle. Now, it's important that we're not finding the difference in the radiuses. We're finding the differences in the area, so we have to calculate the area of those circles. Okay, so when we rotate that object, notice that we're going to get this donut shaped here. Okay, so the inside of the circle that is going to be generated by the green function, the inside function, and the outer edge is going to be generated by the blue function. Okay, there's an animation that shows how we get this as well. So what's important then is when we do our slices, that it's important to recognize what type of slice area that we have in our slice. And it's different if we have a circular slice, okay, or a disc without a hole, or if we have a disc with a hole, because the areas those two areas are going to be calculated differently. Okay, so I'm going to come up with the area of this washer. So this area of this washer is going to be based on the outside radius, which I'm going to call R, and that's going to be based on negative x squared plus 8x minus 13. I have this inside radius, which I'm going to call small r. That's going to be based on the other parabola, x squared minus 8x plus 17. So if I want to find the area of the washer is going to look like this. If I were to generalize then, it's going to be the big radius squared minus that small radius squared, okay, and times by r, because big R squared minus small r squared will give me those two circles. And the difference of the areas of those two circles is going to be what I'm looking for. It's going to end up looking like this when I factor out the pi. So that's the area of the big circle minus the area of the small circle. So that's our generalization. And we can then rewrite this with our parabola. So this is going to be the function on the outside. So negative x squared plus 8x minus 13 all squared minus the inside radius function. That's going to be x squared minus 8x plus 17 all squared. So that represents and so we're going to times that all by pi, and that represents the area of the washers that we're looking for. And now if I want to find out the volume of this donut shape, what I want to do is take that area, give it a little bit of thickness. In this case, the thickness that we're going to give it is going to be this thickness this way, which is a dx thickness. And then we're going to write it as the integral. So the volume expression is going to be V is equal to the integral The intersection bounds are going to be from 3 to 5. So when we intersect the green function with the blue function, we get the intersection point x is 3 and x is 5. So those are my lower and upper bounds. I'm going to factor the pi out, and then it's going to be negative x squared plus 8x minus 13 squared minus x squared minus 8x plus 17 all squared. And again, I'm squaring and then subtracting. So because I'm subtracting the areas, I'm not subtracting the radiuses. And then I'm going to multiply that all by a thickness of dx. And then this expression represents the integral that will calculate the volume of this donut that I'm going to generate by rotating around the x-axis. Again, it's key that when we look at these objects that when we recognize what the cross-sectional slice area is going to look like, because it's different. We do this slightly differently if it's a washer, because we're going to subtract two areas. If we have a washer, so we're going to find the area of the big circle minus the area of the small circle, versus a disc where we're just finding the area of the circle. So this expression I will integrate in a separate video. Okay, so I'll show you the steps to integrate it, but this question only asked us to come up with the expression for the volume. So this is our expression in integral form for the volume of that object. So it's important to recognize, and this is a special note, it's important to recognize that there's a difference between subtracting two functions to get a radius. Okay, so in the previous problem, we subtracted, and it was in this question here. Okay, we subtracted two functions to get the distance in between here that represented the radius. And we can tell that because when we cross-sectionally slice that object, okay, so this object here, when we take a cross-sectional slice, that cross-sectional slice doesn't have a hole in it. It is a disc. And so we're going to calculate the area of this disc using the difference in the two functions to get the radius. That length that black line radius is going to be represented by the difference in two functions, the middle line f and the green line g. Now that's a different situation, and we need to make sure we understand that this is different than the one we just did, where when we take a cross-sectional slice, our cross-sectional slice is a washer. In this case, we're going to, although it looks fairly similar, these are two algebraically different expressions. I'm going to take the outside circle's radius, square it, and subtract the inside circle radius and square it. And that is different than f of x minus g of x all squared. F of x squared minus g of x is finding the area of a washer, where f of x minus g of x all squared is finding the area of a disk whose radius is the difference between two functions.